or popularly a circular queue. So the circular queue is basically the circular structure is logical. Actually, it is implemented using a linear array. Array is always going to be linear, and in memory also. It will be linearly stored. Okay, but logically, we are making to work it as a circular, or as if they are wrapped around from this end is wrapping around this front. Okay, so that now my queue can grow like this. This f is pointing here, so this is first element, this is second element, this is third element of the queue, then this is fourth element, this is fifth element. Okay, and this is the rear last element. Basically fifth element is the last element, so it is acting like this. Are you getting? Is it clear?
Yes, sir.
Yes, sir.
This wrapped around concept, see, this is very important. Then you have to understand this thing, because this simple linear array implementation is not going to work, we have already seen. So this is the array implementation we need to work out for implementing queue. Now obviously, in order to enable this wrapped around configuration, we need to update our NQ and DQ operation. Okay, so in order to get what kind of updation we need to have, let us look at this. That, see, in linear, this primitive implementation which we had seen so far, this, if we consider this array of size 6, and now you are currently you are having only 4 elements in the key. So possible configurations would be like this: first, second, third, fourth, starting from the extremely left, or the first, second, third, fourth, starting from index 1 to 4. Okay, 0 to 3, 1 to 4, or 2 to 5. These were the possibilities. You can never have any other configurations where you have 4 elements in the queue on an array, implemented on an array of size 6 in linear array implementation. But in case of circular array implementation, you can have these three and also these three. Like, your 4 element queue can start from element index 3 and ends at index 4. That means this is first element at index 3, second element on index 4, third element on index 5, and fourth element is on index 0. Similarly, this is another possibility. First element or front element is at index 4, then second element is at index 5, third element as at index 0, and fourth element or last element or rear element is at index 1 in this one. So these three configurations are only possible if we implement wrapped around configurations, and these are possible in both. So we'll always prefer this, because that is going to give us the best utilization of memory. Okay, so how to do that? So we need to check that obviously this updation of R and F will be something different now, and this condition of full and empty may be different. Different expression may be needed to represent full and empty, and obviously this initial condition of initialization of F and R may be different. I don't know, maybe same also. So these three things we need to take care of. Other thing, since it is an array implementation, the structure will remain same, but the actual expressions may vary. So let us look at that. Obviously the earlier one would not work, because that is not same. So first, let us see how do I update. Obviously, I think it is quite clear that since we are trying to go back to 0 after n minus 1, in linear array implementation, we had never tried to go beyond n minus 1. But here we want that once I have my last element at n minus 1, then I have one element to NQ, and I have some portion of the array which is vacant, and from Q's perspective there is a space on 0 or 1 or 2, these indices, then my rear should now point to 0 after n minus. Okay, and that can only be done using a modulus operation. So this is obvious. See, in earlier case, r was incremented just by 1. R equal to r plus 1, here f equal to f plus 1. But here, instead of that, we need to use a mod n operation because we want a wrapping round of this. That means it should normally increment f and r from 0 to 1 to 2 to 3. Once it hits the maximum possible value, that is n minus 1, then I should come back again to 0, and that can only be achieved using this mod n operation. Do you agree? Hello? Is it okay? Hello, students?
Yes.
Huh?
Yes, sir.
This modern operation is okay? Instead of just simply incrementing by 1, both r and f should be incremented and then with a modulus n. Hello, anybody else is having some doubt or something? Or should I proceed? Is it okay?
Sir, could you explain that condition again where f equals to n?
F equal to n means?
Like when it reaches the maximum value, n minus 1 index, uh,
Yes.
how, how will we update the r and f then?
That's what. See, what we are trying. If you consider this linear array here, say let's say, is my pointer visible on this left side array? This pointer, mouse pointer, the hand size is visible.
Yes, sir. Yes, sir.
Uh, so suppose this is my empty array. Empty array. I am starting from here. Okay. Now, as I am enqueuing one by one, the R will get updated. So in normal or this linear array implementation, once this R reaches to 5 or capital N minus 1 in general, then I had to stop. But suppose after I have made this entire uh, array filled with 6 objects, then I am dequeuing one object. Here, this 0th object, obviously it will be dequeued. Then suppose this 1 will be dequeued. So now my current queue is from this index 2 to index 5. F will point to 2 and R will point to 5. Now, since these two spaces are available, I want to allow another NQ operation which will be NQing the object here at this index 0. So my R should now, after 5, it should go to 0, and that can only be done using this operation, because 5 plus 1 6 mod 6, what is the value? 0. If you don't use this mod n, you could never go back to 0. Understood?
Sir, then we can use r mod n minus 1 also in the same way.
R mod n minus 1.
R mod n minus
And that you can see that these minute changes will not make any difference. Only several other expressions will update. Okay. But in either case, what is your philosophical need? Philosophical need is to reset the value of R and F to 0 after it reaches to n minus 1 or maximum value, isn't it?
Yes, sir.
So that can be achieved by multiple formulas, but the cleanest formula you have to use. Okay, obviously, if you choose r mod n minus 1, then the these expression may be a different. Then, I mean, accordingly, you have to update. But in any case, what do you want? You want to reset back them to 0, which was not possible in case of earlier implementation. That you have to identify. Okay. Now, what will be our full and empty condition here? I mean, what will be the expression for full and empty? Any idea? Will that remain
Uh,
same? That r equal to n minus 1 and f greater than r? Obviously, this will not be. I mean, the full condition will be something like this: f equal to r plus 1 mod n. Just check. I have given some example. See, this is full condition when I have f and r. This is the most normal situation where I have inserted element from the front, then one by one, and then I have reaches at the end, and the entire array is now full. So I cannot allow any more insertion or NQ operation. So my front stands at index 0 and R stands at index n minus 1. Okay. So then also this condition is getting satisfied. Now this is also a full condition. Here see, just try to visualize imaginary wrapping round. Okay. This is your front element. Front element is at index 3. Then second element is at index 4. Third element is at index 5. Fourth element is at index 0. Fifth element is at index 1. And sixth and last element or rear element is at index 2. This is also a full queue. Okay. So here also this condition, this f equal to r plus 1 mod n is getting satisfied. The extreme right one, this is the third one, third possibility, where my f, the front element is the last, and second front element is at 0th index, third is index 1, fourth at index 2, fifth at index 3, and sixth at index 4. So it's like it starts from here, then go back to here, here. But in all these three scenarios, the underlying array is full. That means we cannot allow any more insertion or NQ. So anonymously, this condition is matching on all possibilities. You can think of any more possibilities which will be almost similar to this basically. These two are extreme cases, and this middle one is something in between them. And say this R may be at 1 and F may be at 2, R may be at 3, F may be at 4. In every cases, this condition will be satisfied. So this is easy to understand that full condition will be represented by this expression here in this particular implementation. Check it. Everyone agree? Student, please respond.
Yes,
Hmm?
yes, sir.
Just
Yes,
check.
sir.
Huh? Just check. See, these three are examples of different ways our array can get filled completely, uh, indicating a full condition. And in all the cases, this particular expression is holding. So we can say that this expression is capable of representing the full condition. Okay. Anyone is having some doubt? Who is creating? I mean, whose background noise is coming? I think someone. Okay. So next, what should be the expression for empty? Will it be f greater than r? That earlier one. Any suggestion?
R equals to F plus 1 modern.
R equal to f plus 1 modern. Let's see first. Let's check whether f greater than r works or not. Okay. So see, this is one typical, the left one. See, this is status at any point of the queue, that the queue is having only two elements. The front element is at index 5 or capital N minus 1, and the rear element is at index 0. That means it is going back to this to this. Okay. Now if we dequeue further, then what will happen? This particular, the element at index 5 will be dequeued, removed, and after that the configuration of the array will remain like this. There will be only a single element which will be left at index 0, and both f and r will now point to 0. Okay. And then in order to make this array empty, we need one more dequeue. Let's say we dequeue this element also. Then what will happen? The situation will become and will be represented like that is represented in the rightmost figure. Okay. So f will be incremented to 1, r will remain at 0, and there will be no real object in the array. So everything will be garbage. And obviously this f greater than r is holding. Okay. So it's fine. But we need to think if there are some other ways that may lead to this. I mean, there are different ways from which we can come to this empty queue condition. And just like we have seen in case of full, huh, there are different ways of making the array full. Similarly, there may be different ways of uh, coming to this position, this empty position, empty queue. Now, in all of them, we need to check whether this f greater than r or whatever expression we are trying to establish, that should comply all possible transition from this type of queue of only one element to queue of zero elements. Okay. Now here, that's why we need to think it very critically. Okay. So unfortunately, there is a counter example which says that we cannot use f greater than r as an empty condition. For example, let's say this is our scenario where I have only one element like this. Suppose it was filled totally from 0 to 5, and then I have dequeued one by one, 0th element, then first, then second, then third, then fourth, and I have reached in this particular configuration where my f and r both is pointing to 5 or n minus 1, and the queue is having only one element. And now what will happen? when I dequeue this, f will now reset to 0, because this is circular or wrapped around configuration. There is no way f is going to point to some virtual 6. It is going to reset to 0. So this will be the scenario. The array will be empty. R will point to 5 or capital N minus 1, and F will point to 0. And in that case, obviously, this is not going to help. Similarly, what someone was telling, that R equal to F plus 1 mod n or something like that, you can easily find out. There will be some counter example for that also. I don't have that counter example in this slide, but I can give it to you afterwards. And you can also sell in this way, you can find out. Okay, that R equal to A plus 1, just like this, you cannot use the similar kind of expression. Okay, uh, for um, now, so we need to think a bit that what should be the full and empty condition, and accordingly whether what should be the initial condition for f and r. Any suggestion? Students, any suggestion? Hello, are you there or you have left?
Yes, sir.
So
Yes, sir.
so what should be, what do you suggest, what should be the empty condition then?
Can use another condition, like if f is equal to r is equal to n minus 1, then the queue is not empty. Sorry, the queue is empty.
F equal to
R equal to n minus 1, then we can make a special condition, special statement for this one, because only in one condition this is getting, the condition is not working, what we have
okay,
written.
I understand. That may work fine, but see what I suggest. The biggest advantage of this type of array implementation is not only that array is random access, but this kind of implementation is offers a clean coding also. And it's not only clean coding, the number of comparisons you need to make will be very less, because this comparison here, if means we have to perform a comparison. Every NQ operation has to pass through this if condition. Similarly, every DQ operation has to pass through this empty check condition. Okay, so if we make these two conditions very complex, then ultimately in practically we'll lose, because every time I have to check, and every time I NQ or DQ, this condition checking will take much time. So always we need to keep it in mind that we will try to make this condition as simple as possible, that a single computation will say that is whether this is true or false. Okay, so for that, what we can do, we can we can compromise with some uh, extra space, like some single one or two variable I can add, or I can allow leaving one or two single space in the array. I mean, ideally what I should expect, that if I have a array of size 10, my queue should grow up to 10 always, whenever needed. But you can think that some of your implementation may be such that in order to make these conditions very simple, you can sacrifice one or two cells, like for an array of size n, if it is allowed that q can be grown up to n minus 2, no problem, because we are always trying to look at a very large value of n. N can never be 10 for a computer uh, problem. It will be million. So out of 1 million, if I spare two elements to get this expression simpler, I will always prefer that. And that is the philosophy of this particular solution. I mean, I am not saying that solution I am going to give you is the only one, but this is a very very elegant solution which will allow you to keep this expression as simple as this, only sacrificing a single cell position in the array. That means if you have an array of size n, we can have our q to be grown at most n minus 1. It can never be n. Okay. And that is allowed, as I have said, because in computer problems, the n is very large. Okay. So we can easily sacrifice one particular cell. So solution is something like this, that I will change the semantic of this f and r a little bit. Now, instead of pointing to the very first element or front element, my f is going to point one cell prior to that, as shown in this figure. F is now not pointing to the actual front element, but it is going to point one slot prior to that always. This is the semantical change I am making. R is now as usual pointing to the rear element. Fine. And then this will be my initial condition, f equal to 0 and r equal to 0. And in that case, this will be the simplest possible condition we can have for empty, f equal to r. You just check it. I am giving you, I am going to stop after one or two slides, and this is an exercise. Just check. That's so simple. It is giving us the advantage of wraparound configuration. That means we can enqueue as many elements up to n minus 1. Whenever there is a space and the number of real objects in the array is less than n minus 1, I will be able to enqueue. Okay. So this is achieving the advantage of circular array. And also these conditions are pretty simple. See, f equal to r. I don't need to check anything else. Just changing the semantic of f and changing the initial condition a bit. Instead of f equal to 0, r equal to minus 1, now the initialization will be f equal to 0 and r equal to 0. Clear? Now as an
Sir, I have a
exercise,
question, sir.
huh? Huh?
Sir, excuse me, I have a question, sir.
Hmm.
Sir, if R was minus 1 and F was 0, then in the empty condition, we could have written F if F equals to R plus 1 mod n, then also it would work.
You should check it. Huh? Then the next class we may discuss. As I said, that there may be little bit of change here, and we can have same thing. No problem. Okay.
Okay, sir. Thank you, sir.
I am not saying this is the only solution, but what I am saying, uh, always, I mean, this mod n here will be always. I mean, it will be r minus 1 mod n or r plus 1 mod n or r minus 1 mod n minus 1, something like that. It can be there. But this mod of n or n minus 1 will always be there in order to enable this resetting of f and r. Huh? And the wastage of one slot will always be there in order to make this simple. Because if you want that uh, ideal case that you don't want to waste any space, because see, always one slot will be wasted. You can never insert anything here that is pointed out by f. Your queue can grow from here up to this space will be unutilized always in order to make this simpler. Now this exact thing may vary. I mean, as you have said, you can change this expression a bit, and here you can change this expression a bit. But I will prefer that what you are suggesting, just here you are keeping r equal to minus 1. By changing this to that, you will not get any. positive effect. Whereas by making this, I mean changing this condition from f equal to r to f equal to r plus 1 mod something, I mean you are making it a little, at least a little bit complex. So uh, obviously you can see that this is better than that practically, isn't it? Because this will be
Okay,
done
sir.
only
Got it.
once. And as I have said, this every dq operation and every nq operation, these conditions will be checked. So we need to keep these as simple as possible. So our priority should be on these two conditions, simplicity of these two conditions and this modification condition, updation condition. Okay. So from that, obviously, even if your proposal works, I think we should prefer this one over your proposal for that logic. Okay. So as an exercise, you may try that how much complex it will become to prevent the wastage of only one element. Because suppose you want to be very rigid that I am not going to spare any single element. I want my implementation will always allow our queue to grow up to n, size n. Then you will find it is possible. Obviously, I am not saying it is impossible. It is possible, but that will make the definition so complex and I mean practically less efficient. Less efficient in the sense that obviously this when these conditions will become complex and there may be complex checking operations, obviously that will take much more time. Just saving only one single array space and the complexity you are going to add both in coding and in execution time, that will not be acceptable. Okay, but you can try as an exercise. I will encourage you to try. Okay, so it's I think